Hello everyone, welcome back to my channel. Today I am going to explain a recent paper called Siamese X Vector Reconstruction for Domain Adapted Speaker Recognition. This paper was a submission to InterSpeech 2020 and the paper is coming from IBM Research from Israel. And these are the authors, three authors. And in this tutorial we will first cover the overview of this entire paper. Then we will see the specific idea of this paper, which is Siamese X Vector Reconstruction. Then we will see some experiments and results. So what is the motivation of this paper and why do we need the Siamese X Vector Reconstruction for domain adaptation? So basically this paper focuses on something called speaker recognition. So many people will know if you are working in speech, the speaker recognition is basically identifying given audio, whether it belongs to a particular speaker or not. So basically it also falls in something called speaker verification. So given audio sequence or audio data, and you want to identify who is the speaker in this audio, right? So this is a standard problem. People have been working on this problem for almost 30 years. And so the biggest problem in today's machine learning or deep learning based approaches is when you train a model or let's say you train a neural network using some data of database which consists of lots and lots of audio files, and once you train this neural network, let's call it NN, with this data, and it gives you some accuracy, let's say 85% or even 90%, right? 90% accuracy on the test data which is from this database. So basically if you train it on, let's say YouTube recordings, and the model will work very well on YouTube recordings, or if you train it on a clean recorded studio recorded data, so this model will work very well on that particular type of data during testing. But in most of the cases, not only in speech, it even in NLP and computer vision, this domain mismatch will happen during testing. So what is that domain mismatch? As I said, let's say you train your neural network using YouTube data, which is of 16 kilohertz, right? And you assume, let's assume your audio data, whatever you crawled from YouTube, as is a clean data, doesn't have noise or any other music or anything else. So it's completely clean data. And when you train the model on the testing data, it will work well. But when you when you go for the real deployment, let's say your testing, the actual testing data will have some sort of a noise in the audio files, right? It could be background noise or it could be some sort of a background music, something like that. That is one problem. Second problem could be let's say your audio files are sampled at lower sampling rate, for example 8 kilohertz, right? They are like call recordings, and you want to use this neural network on that type of call recordings which are of 8 kilohertz, for example, right? That's another use case. So these kind of domain mismatches or distribution mismatches, this model performance will go down drastically, right? So that is the reason, for example, if you look at Google's speech recognition API, they have a speech recognition API for call recordings. They have speech recognition API for YouTube kind of data, and these kind of different APIs they have created. The main reason is the testing distributions should be similar to the training distribution. That's when the model performance will be good, right? So that is the kind of problem we are facing today. So that is the kind of problems this neural network faces, right? So what is the solution? There are many solutions for this. So one is something called domain adaptation. So the domain adaptation basically says if you know what kind of data distribution your testing data comes from, you somehow modify this model or somehow fine tune this already trained neural network so that it works well on the new testing distribution, right? So that is a domain adaptation, and there are various methods for it. Like for example, there is something called gradient reversal. There is something like something called GAN based domain adaptation, which is basically the discriminator, like the adversarial domain adaptation. So these kind of things, there are various methods for it, but this one focuses specifically uses something called Siamese reconstruction, which we will understand in the coming slides. So that is the main motivation of the paper. So basically, you have a model which works very well on some data distribution, but you want to transfer the knowledge of that model so that it works on some other data distribution. The other data distribution could be, let's say, a lower sampling rate data, or it could be a noisy data. So these kind of things, right? So that is the main motivation of the paper. And as I said, X vector. So you can ask me what is X vector. So X vectors are very famous speaker identification models which are being used these days. I mean, one of the very famous ones, and lot of work is being done on this X vector idea, and many people have used it and written a lot of improved version of X vectors models and so on. If you don't know about it, you should definitely look into it. And I have a tutorial of this X vector model in my YouTube channel. Just search for DNN based speaker identification, something like that. So you'll get the tutorial. So that is the idea, and so we will see that we can improve the accuracy of the new model using this X vector model, which have these problems like noise, sampling rate mismatches, and so on, right? So how do they do it? So basically, the idea is you use a CMS network, which is basically CMS network is basically some sort of a shared neural networks. Let's call it as N1 or NNNet1 and NNNet2. So these two are same neural network which have same shared parameters, right? And so basically what you do is you take the lower take two different X vectors, let's call it X1 and X2, and tries to these are basically low quality. When I say low quality, these are perturbed or noisy testing audio files X vectors, and you reconstruct high quality or high quality X vectors. Let's call it as X1 cap, X2 cap. And how do you do that? You just minimize the reconstruction loss, right? As simple as that. So this is the idea, but it's not as simple as what I'm explaining. It has some mathematics into it. I'll explain those in the coming slide, but this is the main idea. So basically you have CMS network, you try to reconstruct a high quality X vectors from a low quality X vectors, right? When I say low quality X vectors, so the X vectors extracted from low quality data. When I say low quality, the low quality is nothing but noisy or lower sampling rate kind of data, right? And this paper also shows they have a significant improvement over the baseline, and we'll show those numbers in the coming slides. So this is the main idea. So what we have is we have this CMS network here. So this CMS network is a simple feed forward neural network which has three layers. So you can think of them as the feed forward neural network with layer 1, layer 2 and layer 3. And as you can see, the input dimension should be similar to the output dimension, because you are reconstructing the X vector, but you are not reducing the dimensionality of these X vectors. You are trying to reconstruct a high quality X vectors from a low quality X vectors, but you are not changing the dimensions. You are just keeping the dimensions as it is, right? So let's call X1L. So X1L is basically X vector extracted from speaker C1, which is coming from low quality data, right? So low quality, you can think of it as some sort of, it is 8 kilohertz audio data. And also you know that this paper uses pre-trained X vector model which is trained on 16 kilohertz audio data, which is basically a Vox celeb data set. So assume that, I mean, this is the assumption that they are just taking a pre-trained model from Kaldi, which gives you the X vectors, and that pre-trained model is trained on Vox celeb dataset, which has about 7,000 speakers, and it's a very good model, but it's a 16 kilohertz model. But if you want 8 kilohertz model, you can use the other ones which are trained on other, let's say, I think the Fisher or switchboard kind of data set, right? So so this is the idea. So you have X1L, which is a low quality X vector extracted from speaker 1, and you have X1H, which is the counterpart of this X vector, which is higher quality counterpart of this X1, which is also from C1, and but it's a 8 kilohertz, sorry, 16 kilohertz audio. And at the same time you have X2 L, which is coming from speaker C2, and X2H, which is again high quality representation of this low quality X vector, right? So basically this f theta is basically a function mapping. So f, we can think of it as some, f is a neural network and it has the parameters theta, and given x1L, it will give you x1H, and x2H is again function mapping, which is a neural network mapping of x2L, right? So this is the output. Now given the high quality representation, which is this and this, you want to minimize the CME's network loss, right? So basically this yellow and red are two X vectors, and which are fed to CMS neural network, which shares the parameter. I mean, they are actually the same model, but you can think of it as two stream input, but they are essentially the only one. So how do you optimize the model? So optimization is very simple. You get some sort of a loss function, right? So what is the loss function? So cleverly they have two different loss functions here. So one is the reconstruction loss, which is basically, as I said, you reconstruct the minimize the square distance between the high quality representation, which is the ground truth basically, and whatever this predictor from the model. So x1H is basically the I wrote it here as output, but it's actually here they are mentioning x1H is the actual ground truth X vector, and this you can call it as let's call it as cap, right? X1 cap. So this is x1H cap, right, for example. So sorry about the notation, but essentially what you are doing is, so once you map the x1L X vector using function which is a neural network with parameters theta, you get the higher quality representation, and you know the ground truth representation, ground truth X vector, high quality X vector, and you minimize the loss, and you do the same thing for the second vector as well. That is one loss. You can call this as a reconstruction loss. Then they have another loss which is called the which is basically there's some sort of a cosine distance, right? So basically what it says is, if C1 and C2, basically if X1L and X2L are coming from the same speaker, basically when I say same speaker, usually in the data set you will have audio speakers and lot of data for each speaker. You can think of them as clusters, right? So you have if the X1 and X2 are coming from the same speaker, which is either C1 or C2, then you want this cost, or you want this cosine distance to be higher, so that it gets minused out by this 1, right? So that 1 minus 1 is 0, right? So the same thing. So this is just a cosine distance. You want to make this cosine distance more when the X vectors, two X vectors are coming from the same speaker, but if they are coming from different speakers, you want to push them apart. So this actually not only improves the accuracy, also it kind of makes the cluster more better. So I'll tell you why. Because when you use X vector model, let's say you use the pre-trained X vector model, what you usually do is you are just trying to cluster out the embeddings, which are the X vector embeddings. Basically you want to make sure that the X vector embeddings of one speaker, I mean the X vector embeddings of a particular speaker to be tight, the cluster basically, and you want the other speakers embeddings to go far apart, right? So this is the thing you want, and this equation basically imposes uh, that kind of constraints, right? So that is also one of the important thing, right? So this is how the model is created, and once you get this loss value L, you can just use backpropagation and train this model using all the data. Then we are happy and the accuracy will improve, right? So that as simple as that. So hope you guys understood it. So this is the idea of the paper. Now let's look into the experiment section. So for the experimentation, there are two different experiments they are conducting in the evaluation. So first one is they want to find out two different mismatches. One is where the enrollment data mismatches with the test data. So when I say enrollment, think of it like this. So I think many people will be knowing about speaker verification, but if you don't know, I'll just explain it a little bit. So what happens is, in case of speaker verification, right? So you will be given some sort of a development data, right? Some database, right? You train a model, okay? Some sort of a model. It could be any neural network or some sort of GM, UBM model, anything, right? This is a model you have. Now, what I am going to do is, let's say in my company, I want to create this speaker verification system for all the people in our company, right? So I have, let's say we have around 100 employees, and what I will do is I'll call each person and I ask them to read or speak for, let's say 10 minutes, or not 10 minutes, let's say 5 minutes, right? Each of them will give me 100 audio files, right? So 100 audio files. So basically I have 100 speakers, new speaker, which are not seen by this data set at all, and for each person I have, let's say 1000 utterances, right? Okay. Now this is called enrollment data. So what I am going to do is I am going to use this enrollment data and use this developed model and create some sort of methodology, so that when any of these speaker comes and speaks, I can verify whether this speaker is coming from speaker 1, speaker 2, and so on, speaker 100, right? So whatever test data I get in the real field, it's a test data, and before testing we have to collect the enrollment data. That's how Google also does, right? Like for example, when you buy your new phone, when you start installing all the Google's apps and everything, Google asks you to speak okay Google 3 times or maybe 10 times, right? I don't know, maybe 3 times. I just said okay Google, and the phone turned on, right? So see, so that's how. So what happens is, when you speak okay Google to your system, or when you speak okay Google to your phone, when you buy the new phone, they ask you to maybe speak for 3 times or 5 times. So that is the enrollment data for them, right? They use that enrollment data and they create some sort of embeddings using these enrollment utterances for OK Google, and when you next time speak OK Google into your phone, they identify that's you, right? So think of it like this. So Google developed their speaker identification model, right? Once they developed it, when you buy a new phone, they ask you to speak the OK Google keyword 5 times. That is the enrollment. And when you're actually using your phone, when you're, let's say, unlocking the Google Home or whatever, that is your testing, right? So that is all. That's the crux here, right? So that's what happened. So the same thing I'm saying. So during enrollment, you may be speaking these keywords in a very closed room, and there is quiet. I mean, there is completely everything is quiet and there is no disturbance or anything. But when you are actually using your phone, you may be standing in a street corner, or maybe you are in a pub or something, right? So this is the mismatch, right? So that Google should be able to handle all these kind of mismatches. So that is one kind of mismatch, and the second kind of mismatch could be, I mean, it sometimes happens. I mean, your enrollment data could be 16 kilohertz, but your testing data is 8 kilohertz. Rarely it happens, but you can actually you can think of these kind of use cases. Sometimes happens, right? Let's say you develop your model using some open source data and it's all 16 kilohertz, but you want to actually use it for some production in your company, but it's all 8 kilohertz. How do you do that? How do you take care of this kind of problems, right? So this is another use case you might find, right? So that is one thing. Second form of evaluation they are doing is your testing and your enrollment, they are actually high quality. Both of them are same quality. When I say high quality, they could be of same quality. It could be low quality or high quality. When I say low quality, it is maybe 8 kilohertz or for a 16 kilohertz pre-trained model, right? And so that is the enrollment, and sorry, that's the, so that is the second form of evaluation. But the as I said, so let me rephrase it. So that first form of evaluation is you have different types of mismatches between your evaluation and test itself. In case of second evaluation, your enrollment and test are same quality, but your model itself could be of completely different quality. Like as I said, if your trained model, the X vector model, is a 16 kilohertz model, but your enrollment and test data is 8 kilohertz, that's a completely different setting, right? And this paper evaluates these mismatches or these problems with the different types of mismatches, which is your mismatch could be, your test could be having noisy data, your test data could be having different sampling rate, and your test could also be having some sort of a completely different domain, like for example telephonic data. Like as I said, in your training data could be coming from YouTube and your testing data could be coming from telephone calls, right? And for the evaluation they compute EER and min DCF, detection cost function, and all the experiments are conducted on speaker in the wild dataset. So this is the baseline result. This is, you can think of this results as some sort of a lower bound. You can't cross this result. Why? Because you have enrollment which is of 16 kilohertz and testing is also 16 kilohertz. This is the year you are getting, and your model may also be trained. X vector model is trained on 16 kilohertz, and this is the min DCF. And if your model is trained on 8 kilohertz, enroll is 8 kilohertz, test is 8 kilohertz, you have word error rate which is a little bit bad, right? So let's see some of the results. so let's say your X vector, which is the X vector extractor, the pre-trained model, is trained on clean speech, and the test data is noisy, right? If you use the original enrollment, which is not noisy, then your results are a little bit okay because your baseline is good, 5.4 is okay. And if you use core normalization, you will be a little bit better than baseline. And if you use the PLD adaptation, it is a little worse. But if you use this method, the Siamese reconstruction method, your results are very good. And if you combine the Siamese reconstruction along with score normalization, you get the best results, both for noisy enrollment data and the clean enrollment data, right? So second thing is, imagine you have this speaker in the wild data, which is basically coming from some sort of a let's say YouTube, some source which is clean, but you want to what you could do is you just take that data and pass it through phone simulator, right, or telephone simulators, which are available already in the market. So you can just freely available. There are couple of papers also written on this. You can just take some of these simulators and then pass your data through it, and you get the simulated telephonic data, right? And if it is if you use original, you will get 5.2 EER, which is okay with the current approach. But if you simulate it, it is going to get a little bit bad, right? Obviously, right? And and one more thing I want to mention is I am actually working on writing code for this paper. It shouldn't take much time. Only thing I should write is extracting the X vectors from a pre-trained model, then writing this CMA's network, and that should be it, and I am going to release it as soon as possible, working on it. I think in a couple of days I'll release it. And thank you so much for watching this tutorial. If you like the video, please give a thumbs up, and if you're not subscribed to my channel, please subscribe for more video content. Thank you.